I think it's about time to get started. I'm Cliff Lynch, the director of CNI, and it's my pleasure to welcome you to this project briefing session, which is part of our spring 2020 virtual meeting. The virtual meeting is now about midpoint. It started at the very end of March and it will run through the end of May. So we have lots more interesting things to come. We'll have a presentation today from Yi Yang, and following his presentation, we will take some questions. Diane Goldenberg-Hart from CNI will moderate the Q&A. You have a Q&A button at the bottom of your screen, and you're welcome to queue up questions at any point during the presentation as they occur to you. So please feel free to do that, and we'll answer them all at the end. So this session deals with some very interesting issues around the application of some sophisticated technology to digital preservation. And I guess one of the things that's always struck me is how when we work with digital preservation, we are in some ways able potentially to capture more than we could from the originals. We run into some very complicated questions about how to factor that into the presentation process. And I think we'll see a very interesting angle on that today. So I'm just delighted to have Yi Yang with us from Penn State, and he'll be reporting on some joint work with a number of colleagues at several institutions. And at this point, I will hand it off to Yi. Thanks for joining us.
Okay, thank you, Cliff. Hi, this is Yi Yang. I am engineering faculty from Penn State, Abington campus. My presentation is Advancements in Digital Preservation, Spectral 3D Reconstruction of Impressionist Oil Paintings. This project is a collaboration between, among actually four universities or four campuses. So we are Penn State, but we are collaborating with Penn State Department of Art History, and we are also collaborating with New Jersey Institute of Technology and University of Delaware. So we have two art conservationists or art conservators from University of Delaware providing really critical consulting to us. So I'll start the first introduction. So why 3D preservation? So when we originally thought about the project, we first thought about, well, we have a technology and it was really used for our biomedical applications. So the technology is called the optical coherence tomography, and I think it was first invented in the 80s, and it has been very popular now for examining eye retinas. And then the nice thing about this technology is it can both image the topography or the surface profile and the underlayer information, which is really rare for other technologies. So we thought, well, can we apply this technology to artworks? And if you have a really nice 3D profile or capture the 3D profile, surface profile of artworks, basically we can create a 3D model. And once we upload this 3D model with today's technologies such as a virtual reality and augmented reality, you can actually have a completely new experience in viewing these artworks. And we never foresee this, but actually this becomes more relevant for today's education system, because if everything is taught online, then having a more, I guess, interesting or a new method to present artworks would be something I think valuable to education, higher education. The second part we thought about this technology or the applications of this technology is to help the visually impaired to understand art. Because if you really think about, if you most of these artworks, let's say, Impressionist art, which have very unique brush strokes among different painters. And how would you convey this information to someone who is visually impaired and can never see this art? And I don't think they are allowed to touch the art. So what we could do is we can capture the 3D surface profile, and then we can 3D print these artworks, and so that someone who is visually impaired can actually touch them and really get a feel of the difference between, for instance, Van Gogh's brushstrokes and the pointillism by Strauss. So this is another application. And the third application is because the OCT technology can capture the underlayer information of artworks. So it becomes a very valuable tool for art conservation. And this has been, there's multiple papers on this, but it would be one of the aspects we can apply this technology to. And the last scenario we thought about is, if you really think about the really valuable artworks we have today, there's only one physical copy. I mean, we do have 2D images of these artworks, even in extremely high resolution. The problem is 2D image only capture a fractional of what is really embedded into those paintings. And having a 3D high resolution imaging system would give you a lot more data. So for instance, a 2D image of a picture might capture, let's say, a few gigabytes of data, and that's a lot of pixels. But for the technology, for instance, the OCT technology, a painting of the same size can easily go to 3 or 4 terabytes. So that's a lot more data than what a 2D image of like a camera can capture. So we're really thinking about capturing the high quality digital copy that hedge against the worst case scenario. Okay. So before I go any further, there are other optical methods to capture the 3D surface profile. So I just listed a few of them right here. So there's like laser triangulation, struck light, laser scanner, time of flight sensors. And most of these sensors, the biggest issue is a resolution. So they're either lacking resolution or lacking the field of view, which is the amount of space or size you can capture. And another unique feature about OCT technology is that OCT can capture the underlayer information, which none of the current technology is capable of. So here is I'm just going to give you a very short introduction of what is OCT. So here, as you can see, OCT is essentially a laser beam split into 2 arms. So one arm is split to send and is sent to the sample, and another arm is sent to a reference. So if we know exactly where this reference is, we know that exactly what is the distance from our, let's say, a reference point to this arm. And meanwhile, if there's a small change on the surface of our sample, then we can measure the time difference it took between our known distance and the distance we're trying to measure. And by that time difference, we can basically calculate what is the surface profile of this sample. So that's a very kind of amateur explanation of this technology, but that's a basic idea. And interestingly, this technology was actually used for identifying the gravitational wave. So this is essentially a microson interferometer. So the same concept was used. Here we use it to capture images, but if you enlarge this to a couple miles, it can be used to capture gravitational wave. And this is a commercial OCT system you can see here, and you can buy this off the shelf right now. And most of these technology are currently only used for biomedical applications. And for most biomedical applications, we are only looking at a very small sample size. So the field of view of OCT systems are very limited. And in most cases, the field of view is about 1 centimeter by 1 centimeter. So that is clearly not the ideal system to image the surface of the artwork. And we did some preliminary study in the 2006. So that's our first proof of a concept system. So we were able to capture, for instance, over here, the surface profile of a 1 cent coin. And here, as you can see, this is a surface structure image. And then we also capture the topography image right here. And basically, we built a 3D model of the surface of the 1 cent coin, just to prove that this technology can be used to capture surface topography data. And of course, here are a couple more images. They're probably not as intuitive, but this is basically, if you look at a painting, this is an intersection between two brush strokes. And we can also do what we call a cross-sectional cut, because once we capture everything in 3D, we can do layer analysis, we can do cross-sectional analysis. So we did a cross-sectional cut on this layer, and you can see the two brush strokes have a height difference. So these are like two paint brush strokes painted at different time intervals, and one is higher than the other. And what we also did is we did what we call a layer analysis. So as you can see here, we took this we took this painting sample, and then here's a very small region. It's about 1.5 centimeters by 1.5 centimeters. We took this image and then we use OCT to scan this image. And as you can see here, as we peel off, so if you look at this, so C, D, E, F, these are basically what we're doing is a layer analysis. We're peeling layer by layer, and we're trying to see what is a height difference. And as you can see, as we start to peeling layers, eventually the color becomes relatively close to each other, which means the layer between these two are essentially the same. And as you can see here, we also build a surface topography. And as you can see, this layer, this brush stroke on the left-hand side is much higher than the one on the right-hand side. So this is our first try to build a proof of concept system. However, the system we built had severe limitations. And the most important one is a limited field of view, because the system we are really designed for image and eye retina. And we just kind of, put in some samples to art painting samples, but we couldn't really scan anything that's larger than 1.5 by 1.5 centimeters. And we also have a huge amount of data need to process, and the system was relatively slow. So this is what our original system. As you can see, we have our very small painting here, and it only samples a very small size. And this is our OCT sampler. So what we need to do is we need to enlarge our scanning area. And what we did is we built, we purchased this off-the-shelf robotic scanning system. And it's a XYZ system. So we can scan, we basically increase the size from 1.5 to 1.5 by 1.5 centimeters to 2 feet by 3 feet. So this is our maximum scanning size we can scan. However, in our experiment, we didn't really scan a painting that large, because the amount of time takes to scan that a painting with that size would take us almost a week at this point. So we only scanned a very small sample size to prove the concept. And this is our first sample. So we asked a New Jersey-based artist to paint oil paint on a canvas. And the size of this paint is 10 centimeters by 10 centimeters. The style we choose was based on, we want something that looks like a Van Gogh, because we are very, very interested in the unique brush strokes of Van Gogh's works. So the artist was very happy to have these brush strokes, and tried all different different colors of paintings, and painted at different time intervals. And once this painting was created, we wanted to scan part of the painting. So this dotted box here the white dot box is the part that we actually scanned. And the red box here is the field of view of our OCT system. So as you can see, our strategy is to, every time we scan a red box, then we move the red box to another location and scan another red box. And we would move about 9 times in the vertical direction, and we have to move about 10 times in the horizontal direction to be able to scan the image of this white dotted box. But the problem is, it also created a lot of problems, and I'll talk about this in a second, but I'll show you the first preliminary data. So the preliminary data, so for OCT system, basically we get 3 different scans. We have what's called the A scan, which is just a vertical signal. And then we call it the B scan, which is essentially the cross-sectional image. So as you can see here, the image in B here shows the cross-sectional image. And the surface here is basically the surface profile. And we are also able to see the underlayer information. So for instance, if we have older artworks which have like multiple layers, we should be able to see like the layer information. But because of this paint is so new, the paintings didn't really have time to, one layer of painting didn't really have enough time to dry before the other painting was applied. So we weren't able to see the clear layer information yet. And the figure C represents the on-face image, which is what we see from top to bottom. So this would be like a very typical 2D image, but just in gray scale. And of course, we can now construct our 3D surface, and this is what it looks like for one OCT scan. So what happens is we need to, we have to capture multiple of these surface scans, and we have to stitch them together to make a larger image. Yeah, I'll talk about this. So this is a surface profile. So if you look at this original painting here, so the white dot here is an area we want to capture. And basically what we have to do is we have to use the OCT to capture multiple areas encircled with a red triangle. And then we have to digitally stitch them together. But here's the problem. Because our system, the scanner is a mechanical system, and whenever you have a mechanical system, it introduces error. So now the problem is when we move these steps, there's gonna be overlaps, and we cannot really control the exact amount of movement of those overlaps because of simple mechanical error. So what we had to do is we had to come up with a software to actually identify which part was overlap and digitally trim the image so that we can make a perfect stitch. So that was actually almost 50% of our work, is really coming up with that algorithm that allows us to do digital stitching. So once we finish digital stitching, as you can see, this is our finalized product. So here you have, this is our stitched picture, and on the right-hand side is what we call the topography image. So the topography image here represents the actual height information in grayscale. And as you can see, we still have some artifacts like between one, so we're doing vertical scans. So from one vertical scan to the other ones, you can actually see there's still some artifacts. And we're actually currently working on to remove this artifacts digitally. But this is a much easier problem than remove the overlapping images. So now once we created this topography image, which contains all the surface height information, what we can do now is we can transform that information into almost like a mapping. So we actually used a very similar technology as how they do, like how Google Maps topography. Basically, if you think about how the height information is mapped from Earth, right? So basically a LiDAR, a satellite shoots like LiDAR waves onto the ground, and depending on how much time it took the LiDAR or the laser signal to return to the satellite, you create the Earth's surface topography. So that's pretty much exactly what we did. We basically create the surface topography of a surface of the painting, and then we were able to create the same kind of image, surface topography image, as how Google Maps create for Earth. And once we have this topography image, what we did is we also took a 2D picture of the image, which is basically a spectral picture, or blue, green, and red, blue, and green images. And then we kind of projected the color image upon the surface topography image, and to create our 3D spectral digital reconstruction. So now this is our model. We do have a 3D model on my computer, but we just tried this, and the problem was Zoom and both the 3D engine, it takes so much resources, and it just froze my computer, so I can't really do a live demo. But this is what you can do with this digital reconstruction. You can basically rotate this thing, rotate the sample. You can zoom in and zoom out. And yeah, so this is a very interesting viewing experience, because if you imagine in future, this 3D model can be directly sent to a virtual reality or augmented reality device, and the users can actually rotate them, look at the details, and zoom in and zoom out. So again, just to reiterate, we started off with a painting about 10 centimeters by 10 centimeters, and we choose the region of interest just because of the time. We have, because the OCT system we are using are actually borrowed from the biomedical opticals group. So they only gave us a very limited time window that we can use the system for art application. So we did only have enough time to scan the image encircled in the white dotted area. And this is our digital sample. So then we thought, well, we can now actually do 3D printing. So we took the digital sample we collected, and we used a 3D printer to print the sample. And as you can see, we print a couple of samples to see. There's a couple of variations we need to adjust. But this is one of the samples you can see. It's exactly the same size as the original, the area on the painting. And you can see the, the surface topography data here. And now you can actually touch them. So if you really want to, if someone is really visually impaired and want to really have a feeling of what Van Gogh's painting feels like, well, now we can give that person this sample, and they can actually touch this. So I think that's pretty much all for my presentation. And this is our references. Oh yeah, so acknowledgement. And so we really want to thank Dr. Christine and Brian for their really critical support, because both of them are art conservators, and they really provide us a lot of information. Our group is an optical engineer group, and we have no experience in art. And they really helped us to understand a lot of the concerns or the problems. And the painting sample was produced by a New Jersey-based artist, Katie Wallace. So she did a really good job. And again, I really want to thank our sponsor, the Crest Foundation. They really took a chance on us because we had no track record in this area. And without their funding, we would never have this product or this experiment. And part of our funding also comes from NSF. So thank you so much. And I'll take any questions. Thank you.
Thank you, Yi.
Thank you.
That was absolutely fascinating. Quite an interesting process that you shared with us. And we're really grateful to you for coming to CNI to talk about your project. Amazing implications for preservation and accessibility Just incredible. Thank you.
Thank you.
And I also want to take an opportunity to welcome all of our attendees. You are reaching this session as part of CNI's 2020 virtual spring meeting, and we're so glad you could join us. Thanks for making time out of your day to be here with us. And at this time, I'd like to invite you to type in your questions in the Q&A box, and you will be happy to answer your questions, or if you have any comments, if you are thinking about some kind of applications for this technology, or you're wondering about some of the specifications, this would be a great opportunity to share those with Yi and get some of his firsthand knowledge about this kind of technology. While we're waiting for those questions to come in, I just want to share with you via chat there that, as I said, this is part of CNI's Spring 2020 meeting, which will go on through the end of May. And I've just shared with you the direct link to our schedule for the project briefings yet to come. There are many, many more to come. So check that out and hope you can join us again. I was wondering, Yi, what's your estimate for the amount of time per artifact that it would take to create one of these scans?
Yeah, so the current, the area we did, I would say it's about, it took us about, let me think, about 30 minutes. But if you really think about scale up, that actually takes a lot more time. And it really, I think there's a lot of mechanical improvements we can improve on, and which really increase the speed. So really, speed wouldn't be the biggest concern for us. I think the biggest concern for us is data. We are really looking at terabytes of data. And when you're talking about that kind of a scale, processing them in real time or even post-processing takes a ridiculous amount of resources. We are already using independent graphics card to process these data, like GPUs. So yeah, processing data would be a very resource intensive problem.
Yeah, I can imagine that. And I'm curious to know, is that those resources, are they centrally located on your campus, or is that something you have in your department, or where are you getting those resources from?
Well, for currently we can handle in our lab. So we have a couple really powerful computers, and also like I think one of the revolution is how the independent GPUs the price has dropped. Because a couple of years ago, those things are very expensive, but nowadays a very powerful GPU with 3,000, 5,000 cores can cost like $2,000, $3,000. So that's actually a lot more affordable. And for image processing, most of the processing is actually pretty standard. So it doesn't really, it's a very repetitive processing. So a GPU is actually a very ideal tool to process image information.
I see. Okay. And the data you're storing locally as well, even though that's massive amounts of data. I can imagine that it multiplies very quickly. And what level of expertise would be needed to create these kinds of files?
So that's actually another project we're working on, is really trying to come up with a software that actually simplifies the whole process, because the system right now, we build everything in lab, so in-house, and it's really, we need to have a technician or a grad student who has been trained on the system for at least a year to be able to carry out all the works we wanted to carry out. Yeah, we definitely need to work on the software and the hardware optimization. But but we are looking for future collaborations. We are thinking about just driving up, move the system to whatever the location, and we will do all the scanning for them.
Okay, I see. So you don't see this as necessarily being a system that institutions could adopt and deploy?
Yeah, it would be very hard, because anytime whenever you have optics, something could go wrong, and it would take a technician days just to readjust everything. So optics is a very interesting field that it's very hard for optics to be popularized, I guess.
So interesting. Well, I don't want to, it's fascinating as this is, and I have a laundry list of questions I'd love to ask, but I don't want to make anyone feel like they don't have an opportunity. So please, if you have questions, I see several folks are still with us here, even though we're slightly past time. But if you have any questions for Yi, please feel free to type them in. And we also have the ability to turn on to unmute attendees. So I think what I'm going to do now is, with thanks again to Yi and to our attendees, I'm going to go ahead and close down the public portion of this presentation. I will turn off the recording. And if you'd like to hang around a little bit, Yi and I will still be here. If you'd like to sort of approach the podium and have a one-on-one chat with Yi or make a comment, please feel free to do that. And thank you again, everybody.